All right. Thanks. Thanks to Byron for the introduction, and Byron and Joshua and the other organizers for inviting me. This is by far the fanciest lecture hall I have spoken in quite a while. I'm especially happy that you are here, since there is nothing more awkward than an Italian speaking English with an heavy Italian accent in front of a bunch of other Italians. So I'm really happy that there are some more not Italian speakers here. Before I start, I have, for contract reason, to acknowledge that at present I am funded within a grant by the Polish National Science Center, and I belong to the Philosophy of Physics group. So this was like the short YouTube advertising you had before your videos. Now let me start the talk. We will discuss the following question. Do mathematical facts have physical effects? So by a mathematical fact, I mean roughly a fact such as the square root of 9 is 3, or maybe a fact like a particular point in a given Riemannian manifold has curvature R. Do such facts cause anything in the physical world? Another way to put it might be, do objects such as numbers, sets, and functions, do they interact with matter and influence its behavior in any way? So a theory of this sort is sometimes associated to the ancient Pythagoreans. So supposedly, we don't have many first-hand accounts, but for example, if you take one number and you sum all its divisions, all the numbers that divide it, you get a number. But if you do the reverse, you take the second number, you take all its divisions, and then you add them, you get the first number. Then you said that these two numbers were friends. And maybe the fact that these two numbers were friends adds some implications. So maybe people are associated with some number, and that has some influence in maybe their lives. The set of mystical ideas are sometimes called numerology. So I was reading some time ago, maybe watching a video by the famous singer and songwriter Taylor Swift, and she was explaining to the interviewer that she's particularly associated to number 13, and then the number 13 is supposed to have some sort of properties. It's kind of associated with kind of rapid changes in your life, and that explains, I don't know, something about why she's with that boyfriend or then that other boyfriend, something like that. So this kind of idea that numbers are connected with what goes on, say, in the physical world, maybe even in your life, that's called numerology. It's usually considered kind of a mystical view. For that reason, philosophers do not take it the question very seriously. It is considered to have an obvious answer, which is the following, which is obviously not. Are you gone completely mad? But what I would like to do in this talk is to defend, or at least show that under certain conditions, there might be good reasons to believe in an affirmative answer. So why do philosophers reject the view, and why does it matter? Well, it's not very clear why. It's not often given an elaborate defense. It is kind of usually assumed not to be the case. For example, this is a quote from an influential book from the 1990s by Mark Balaguer, called Platonism, I think, in anti-Platonism in the philosophy of mathematics, that has been often cited. So in the passage, Balaguer says that science does not assign any causal rule to mathematical entities. Thus, it seems that empirical science predicts that the behavior of the physical world is not dependent in any way upon the existence of mathematical objects. Which he goes on to say, as a consequence of that, he suggests that, given what science says about the world, then in some sense what it tells us about the world doesn't depend on what the mathematical tools it employs or the mathematical claims that come with it. Its picture of what the world is like would be the same if there were no mathematical objects at all. Therefore, if you really want an argument for the view that mathematical objects have no influence, or as Balaguer says, that what goes on in the physical world, say in Taylor Swift life, doesn't depend in any way on the number 13 or any other mathematical object whatsoever, is because science. We believe the picture that science gives us, and according to Balaguer at least, and this has been repeated and repeated and repeated ad nauseam, according to science, mathematical objects have no causal rule. Well, this is the claim that I will attack. It seems to me that there is actually a good case of exactly the opposite of what Balaguer says. That according to science, if you take our theories seriously, our best physical theories, for instance, they do tell us that mathematical facts may have actually quite an influence. Before I get into the details, let me do a disclaimer. So I've been talking about cause and effect, but I will understand these terms rather broadly. So when I say causation, just to be brief, I will mean what some people call, say, usually effective causation, whatever, the rock, breaking the window, this kind of cause and effect, as well as some people call metaphysical causation, say ground or ontological priority, or some sort of genuine dependence. So I will use causation for simplicity to mean either metaphysical causation or effective causation. And then we can decide, okay, which one is it? I'm actually more sympathetic to just straight effective causation, but that's not what I will defend. Let me return now to the question, the key question. So what does science, so our best science, our present science, in particular physics, what does it tell us about the efficacy of mathematical objects? Well, it turns out that there is actually a tradition among some very distinguished physicists. It actually goes in the opposite direction. For instance, if you read, you take just the incipit of the Traité analytique de la chaleur of Joseph Fourier, he begins with this quote, which is often attributed to Plato, et ignem regunt numeri, which is usually translated by as, and fire is also governed by numbers. Or maybe we might translate it by saying fire is also ruled by numbers. And there is a tradition that probably goes from Plato's Timaeus, probably to Kepler, to Fourier, and continues actually very much to the present day. So oppose like Balaguer's quote with this citation of Roger Penrose from his 2004 book, The Road to Reality. Penrose says, the more deeply we probe the fundamentals of physical behavior, the more we find that it is very precisely controlled by mathematics. So once again, let me repeat that I will understand causation broadly. So it could account for this idea of Penrose controlling the physical world, as well as Fourier ruling or governing what happens in the physical world. Now, the question is, okay, how do we settle the dispute on one side between Mark Balaguer and nearly all the contemporary philosophers on one side, and Fourier, Penrose, and Taylor Swift on the other side? What I will give you is, and the main object of, say, the paper that goes with this presentation is an argument for the view that mathematical facts exert an influence on physical goings on. However, to be extremely precise, I'm not going to defend that actually mathematical objects or mathematical facts do influence the physical world. I think we should take that seriously. What I will defend is just a slight weakening of that. There is one way, but only one way, in which I think we might reconcile physics with the what we might call the received view, that mathematical objects are inert, or that they are isolated, causally isolated from us. But it requires a bit of presentation. So this is the following definition. So to nominalize a physical theory means, when I say that, what I mean is I want to give a formulation of the theory that does not quantify over, or say, does not refer to mathematical objects at all. So a theory can be nominalized, general relativity or classical mechanics, if you can formulate it in such a way that I can explain everything that the normal mathematized theory, mathematical theory explains without referring to mathematical objects at all. So a theory can be nominalized under those conditions. Now, what my thesis is, to be spelled out completely, is that if we cannot nominalize our best physical theories, and of course, if such theories are true, then I will argue that mathematical facts about, in particular, mathematical models, which are used, as we'll see in physical theory, they cause, influence, or govern purely physical facts about physical systems in the world. All right. This is what I will defend, and I will proceed to the argument. Let me just say that if you have a comprehension question, just stop me, because I think I should be able to present things very, very comfortably. So if you don't understand something, well, let me proceed to the argument. First thing I will do is to be a bit more precise in what I take a typical physical theory, and this will encompass most physical theories you would find in any branch of physics. What does it look like? I will make a few assumptions about that. So I will assume a version of what is sometimes called the semantic view of fields. I actually think this view should be acceptable to a very, very broad class of people, even if you like, say, the syntactic view of theories or some other favorite pet theory of yours. This, I think, should still be relatively uncontroversial, but it should be super familiar if you know the semantic view of theories. So we'll assume the following. Physical theory consists of two things: a class of mathematical structures, collection of mathematical structures which are used to represent the physical world, together with what some people call, and I shall refer to here, as a commentary. And the commentary is like, well, an explanation of how the structure in question is supposed to represent the properties of some system in the physical world. Example, well, this is a rather fancy example, but let's run with it. So take, say, the theory of general relativity, which you could call PGR. Well, the formalism of the theory, so the models of the theory, well, consists of what? Well, you could take it to be what I call semi-Riemannian manifold. You really won't need to understand the details, but if you do, maybe it's a useful example to keep in mind. So some sort of pairs of a smooth manifold and something called a metric, GAD, to which you add something called tensor fields, which are supposed to represent the C method. From there, you can define other tensors called GA and TAB, so the stress energy and the Einstein tensor. And then you can pick out, essentially, among all these structures that have this form, you can say that the models of the theory are the subset that satisfy a certain equation. At minimum, you would have the famous Einstein field equation, which are represented here. If you have no idea what this is referring to, don't worry, probably doesn't matter much. But it's an example of, it should be give an idea that, a physical theory is a class of models which often is defined by the equation of the theory. All right. Now, if you have the formalism, you have just a bunch of models, you don't have yet a physical theory. You want to interpret it, and then you want to have an account of how it represents something in the world. So you might say, okay, what does it represent? And then you say, well, I assume that in the world there are something called space-time points and space-time regions, which you might think like as aggregates of the points. And then we assume that some regions are filled with matter and fields. And of course, that the points are arranged by some geometrical relations. This is yet very vague, but we can turn it into some precise way by what I call a correlation postulate. So what does the theory say? Well, it tells you the formalism. Now, I just gave you a brief account of what's supposed to be in the world corresponding to it, but the precise claim is that the models represent how these physical objects are arranged. How? Well, we assume that there is some sort of correspondence, so like a one-to-one function, possibly not one-to-one, maybe just injective function, which associate to the stuff in the world, the matter and the sort of space-time points, so the matter and the field, some representation, some objects, some correlate in the model, so it represents something in the model, such that whenever two objects in the model stand in a certain mathematical relation, while the corresponding object in the world stand in some physical relation. So this is like the very simple picture, right? Imagine that you have the space-time points are supposed to be the physical objects, space and time that we inhabit. They are associated to manifold points, which are really mathematical objects. They could be couple of numbers, say. This is the example. It's like a picture of what the correspondence would be like. Or you might imagine that, say, to make the correspondence in the case of general relativity, what it would be like, well, you might associate to, say, the possible trajectories of the particles. They correspond to what are called time-like geodesics in the manifold, which are what? Well, they are basically curves or functions from the real numbers to the points of the manifold. Then you have geometrical properties of those paths or possible trajectories, like the time it takes to move on that trajectory. They correspond to mathematical properties. Say, the number you get when you integrate the metric along the path. Longer the time, the longer, say, the higher value of the integral. Or last example, you have the physical space-time, which is represented by the mathematical space-time. And the idea would be, well, the physical curvature at various points, well, it corresponds to the mathematical curvature of the model that represents. You can have a more detailed account if you take, for example, Malaman's book on the foundation of space-time theories and Newtonian gravity, and then, his first chapter is mostly, first he presents the formalism, tells you what all these kind of mathematical objects are mathematically, and then he gives what basically calls this kind of correspondence postulate, what he calls interpretive principle, which tell you how these things would correspond in this way, would mirror the properties of the physical system in the world. All right. A few things about this. So I hope, if you have followed me so far, so I have not lost you, that what the theory seems to be saying is that there is some sort of correspondence, or what I would call a correlation between the properties of the model, the properties of some models, and the properties of the physical world, or the physical space-time in this case, between the mathematical geometry of the mathematical model and the physical geometry of the physical space-time. Now, what I would like to say is that such correlation or such a correspondence is nomologically or physically necessary. There is a sense in which space-time, physical space-time, couldn't have failed to correspond to some model of general relativity. Right? It must correspond to some model of general relativity. It's a law that it does. General relativity would be false if there weren't such correspondence. However, it is not in any way either logically, mathematically, or metaphysically necessary. So metaphysically speaking, space-time could have been Newtonian, or could have been discrete, or could have been many ways in which it would not correspond in the way I just hinted with any model of general relativity. So the fact that space-time corresponds in the manner I just described to model of general relativity is not at all trivial, not at all a logical tautology, not at all. This is what I think. And I should also specify something very important. We should distinguish three claims, right? There is the fact that space and time, or say a region of space and time, corresponds to that particular model. That is clearly a kind of contingent fact. It could easily change the initial condition, and it could, if you change just your hair by a millimeter, then the exact space-time to which, let's say, the exact model to which space-time corresponds would change. So that's clearly kind of a contingent fact that it corresponds to that particular model. The fact that space-time or any object corresponds to some mathematical model whatsoever, so that it corresponds in some way to some mathematical model, you might argue is completely trivial. That's not what I'm saying. It's not what I'm interested in. Of course, no matter how the world is, it will correspond in some way to some mathematical model. That's as long as the mathematical model exists, and there are plenty of them, of course, it will correspond in some way. As Nelson Goodman says, everything is kind of similar to everything in some respect. So obviously, if you take the mathematical models, the existence of some correspondence is guaranteed. However, the claim I'm interested in is the following. Why is there a correspondence between space-time and the model of general relativity in that specific way? At least one model of general relativity in that specific way. All right. This is what I call the mystery. And to understand why I find that mysterious, why there must be such a correspondence between the world and a model of general relativity, you might compare it to a similar problem that some of you might be familiar with, something called the access problem. This is the maestro, Hartry Field, explaining his version of what he thinks is the problem. And he thought, or at least he thinks, that there is a similar mystery when we try to explain how the belief of mathematicians could correspond to the properties of mathematical objects. He said, the idea is that there is a correlation between mathematician belief states and the mathematical facts. So generally, the idea is that we suppose that mathematicians are reliable when they tell us about mathematical objects. So if they say that P, generally P, is so striking as to demand explanation. It is not the sort of fact that is comfortably taken as brute. Then he says, the Platonists can postulate some brute facts, but what he calls special reliability relations between the mathematical realm and the belief states of mathematician seem altogether too much to swallow. So Field was worried in this question of, we are supposed that mathematician tells us a true account of how the mathematical Platonic world is. There is a correlation between what they say and how the world is. What can account for such a correlation? Well, if you're not familiar with this problem, forget it, it's not needed. But if you are maybe familiar, you can maybe understand my question as roughly similar. Our best theories of the world, they tell us that there is this correlation between the properties of the model and what goes on in the world. One mirrors the properties of the other. Why? Why is there such a special reliability relation? How does the physical world know that it must behave so as to conform to a model of general relativity instead that to a model of Newtonian theory or a model of some other thing? All right, let me turn this vague intuition into a more precise argument. Before I do that, so you might have just one last comparison that sometimes I like to make as well. He says, suppose you have two really disconnected, causally disconnected objects. So in this case, it would be the belief of the mathematician are supposed to be causally disconnected from what goes on in the Platonic world. And he makes an analogy. Suppose that there is an obscure village in Nepal, right? So some or the other side of the moon or whatever, some place that you have no causal contact. But suppose that whatever you believe, you claim that all your beliefs, and you have detailed beliefs about what goes on in the village in Nepal, right? And you assume that you are reliable, so you tend to be right. When you say something like, oh, the mayor is this guy and he has an affair with that other person, something like that, you're always right. That would be very strange. The idea is, it is rather as if someone claimed that his or her belief states about the daily happening in a village in Nepal were nearly all true, despite the absence of any mechanism to explain the correlation between those belief states and the happenings in the village. As you see, we have a similar problem here. We're saying that there is a correlation between what the models say. So the model describes the physical world. They tell us what happens, and in some detail, they contain information about what happens in the physical world. What is the mechanism that explains the correlation? How could you find, say, if you found like a model of the village in Nepal, completely disconnected from what happens in the village, but describes what happens there, what is the mechanism? All right. So this is the end of the intuition. Let me, to conclude, try to put these ideas into a more precise argument. Premise one is the following, which I think I have mostly already argued for. Premise one just says that general relativity posits a correlation between the physical properties of space-time and the mathematical properties of a semi-Riemannian manifold, so a mathematical object. This is what I've argued for at the beginning. Premise number two. This is the premise that I think is behind the rhetorical question, what is the mechanism? And roughly, the assumption is this. Whenever you have a correlation between two or more variables, a variables is just a fancy statistical name for basically any property. You might have a correlation between, I don't know, drinking coffee, the amount of cups of coffee per day you eat, and you drink, and whether you have dementia or not, what would have, any two properties, correlation between, temperature in the room and the reading on the thermometer, you know, any two properties. Whenever you have a correlation between two variables, it is either a complete coincidence, and there are plenty of those. You might have some correlation or correspondences are mere coincidences, or there is some non-causal explanation for the correspondence. It admits of some non-causal explanation. Or there is some common cause or ground. So to pick an example of that, suppose you have a good correlation between going to the hospital and dying, right? If people that go to the hospital tend to die more frequently than the general population, that's neither because, you know, the hospital causes you to die, nor because dying causes you to have been in the hospital, but because there is a common cause, you know, the fact that you are sick causes you to go to the hospital and also to die. So one possibility is that there is some sort of common cause or ground for the correlation, something hidden, which is neither of the two systems which are correlated, but which influences both. Or finally, I will assume that if neither of the above, it's not a coincidence, there is no non-causal explanation for it, there is no common causal ground, well, then it must be the result of causation. Understood broadly, of course, causational ground. All right. Now, 2 is, of course, the key premise. It says that either blah, 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 or blah, 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 or blah, 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 or blah, 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 or what we want. And now, under the assumption that we cannot nominalize physical theory, what is sometimes known as Field's program, well, if we don't have that, we cannot nominalize the theories, then all the other options are ruled out. So let me begin with the first one. Premise number 3, the correlation is not a coincidence. So what would be a coincidence? I don't know. Let's say a coincidence between variables. Say there are some famous examples. I think that for like 20 years, in every Champions League final, you had at least some Croatian player. So you had a correlation between, you know, Champions League finals and there being some Croatian players in some team. That's a coincidence. There is nothing in having a Croatian that causes you to go to the final stage, right? And this is the kind of thing that, or say, there was a famous similar correlation between when a certain team won the World Series in baseball, then say the Republican candidate won the next election, something like this. And this was like for many, many candidate cycles, whenever the team won, then the Republican candidate would win. We assume that there is no causal influence, assume that they are a coincidence. What does it mean? Well, I take a coincidence to be the following, something that could easily have not been the case. So a coincidence is something that, okay, we have seen this correlation in the past, but we have no reason to expect it to continue in the future. But also, we recognize that in very nearby possible worlds, in some sense, very nearby possible worlds, it would have been broken. So that's, you know, it happened, but if things had been just slightly different, and there is some ambiguity, some vagueness what slightly means, but in some nearby possible world, the correlation was broken. It could easily have been broken. So if that's what I mean by coincidence, that's our analysis of coincidence, then I say the correlation between models of general relativity and space-time is absolutely not a coincidence. Why? Because it is nomically necessary, as we said. So this is what is told by general relativity, which is supposed to be your best theory of space-time. Let's take it for the purposes of this talk. Then it would not be a coincidence at all. It's absolutely not a coincidence, say the general relativity is true, at least in the sense which is relevant to drawing causal connections. All right. So coincidence, not plausible. Premise number 4. If Field's program fails, here I should have defined that Field's program is the attempt which has been made, say, by Hartry Field notoriously, and on my little own by myself a little bit, trying to nominalize the best physical theories. Well, if that does not work, then I think we don't have any prospect for a non-causal explanation of the correspondence between the mathematical models and the world. Why do I say that? Well, if we could nominalize a theory, then in principle, as Field shows, we could kind of explain why the world behaves this way without mentioning the models. We could give an intrinsic account of, say, why space-time is as it is, why it responds to matter in that way. We could give an independent account of, say, why the mathematical models are what they are, which is given us by mathematicians. And then we could explain, okay, if we have these two independent accounts, okay, then it follows that they must correspond. And I would call it a non-causal explanation of why they correspond. Well, because they are doing this thing, they are doing separately this other thing, which I can account independently of each other. And given these two accounts, okay, then I can make sense. I can see that it follows that if they're doing this independent thing and this independent thing, then they must correspond. That would be the dream for a non-causal explanation of the correspondence. But failing that, if you cannot have any independent account of what the physical world does, then I don't see any other non-causal explanation. If you have one, I think there is an argument that in principle we cannot have one, but I think it's probably enough. And finally, well, actually I have two other ones. We're almost to the end. There is no common causal ground. Okay, what could be a common cause or common ground for facts about mathematical models and the world? Well, I don't know, unless you think maybe God created independently the physical world and then mathematical models and then established some harmony. We have pre-established harmony between the two. I mean, that could be an option, but even in this case, I think that if you probably believe like that God created mathematical objects, I think that it wouldn't make much sense to distinguish, say, God's ideas of mathematical objects from the mathematical object themselves. I don't think, you know. So barring that, if you're a naturalist, you won't take it seriously anyway. And if you're theologically inclined, I think it probably doesn't work either. What is left? Well, we are left with the following conclusion. So we have barred everything except the last option. So there must be some influence. I mean, if Field's program fails, if you cannot nominalize, either between the mathematical models influence the physical world, or the physical world must influence the mathematical models. So just the last tiny bit is something about that. In which direction does the influence go? This is premise 5. The last tiny bit of the argument is the physical facts do not cause or ground the mathematical facts. And here I just want to appeal. So of course, if you grant me 1, 2, 3, 4, 5, and 6, you of course get 7. So if Field's program fails, which again just means we cannot nominalize, then it follows from what I said, the mathematical facts cause or ground the physical facts. The only tiny bit, the only premise I still need to justify is 6. Why the physical facts do not cause or ground the mathematical facts. And here I just want to appeal to the following principle. The principle is the following. Whenever there is a correlation due to some sort of causal interaction, understood broadly, right? The direction of causation, so which variable influences which, well, the direction of causation grows from the variables we can independently account for to those we cannot independently account for. Let me give you an example to see why the principle, I think, is really plausible. So we have been talking about correlation between models and the physical world. You can compare them to an example of a model representing something, might be, say, a map of a territory. You have a map of, say, Canton Ticino, whatever, with the various position of the various cities, the hills, the mountain, and so on, and the actual territory in the physical world. That's a relation of a model representing what is sometimes called a target. In this case, say Canton Ticino. But you have other examples. So you might have a musical partition. The musical partition represents the piece of music. So I don't know, you have a partition of Schubert's Hellkönig, and then you have a representation between the partition, which is say in front of the musician, and the music. What influences what? So those the properties are the properties of the map dependent or caused by the properties of the territory, or the other way around. So does the territory depend on the map? But you can also ask the same question for the partition of music, right? Is the music, the properties of the succession of notes, is it influenced by the partition, or is it the partition influenced by the music? And here, of course, the intuitive answer are two different ones. Right? In one case, intuitively, the properties of the territory influence how the map is made. But in the case of the partition of music, it is actually the partition that influences how the musician plays. Or to take an example again, Platonic example, the blueprint of the house, right? Is it not the blueprint of the house influence how the house is made rather than the other way around? In general, how do we make the distinction? Well, we see that the causation can flow either way. It can either flow from the model to the target, or it can flow from the target to the model. How do we decide? Well, the idea of the principle is, what can we explain? So which properties can be accounted for independently? The intuition is this. If I want to explain why is Canton Ticino the way it is, either geologically or why our city is located there, I have usually either an historical or a geological explanation for why it is, right? If you ask me why is Lugano here and Bellinzona here, I can give you a sort of historical account of why they were founded there, right? That doesn't refer to the map at all. But if you give me a map of Canton Ticino, say, I don't know, you're probably too young, but if you're some sort of paper map, right? If you want to account for the properties of the map, you cannot do it independently of Canton Ticino. You have to explain, oh, it is a map of that, and some guy or some person collected information about this object and then kind of transferred them to the paper. So the explanation of why the map is as it is cannot be made without referring to the target. So you see in this example that the causation, like the order of causation, is the same as a kind of the order of explanation. It is the same in the partition case. So if you want to explain why the music is as it is, so why is the musician playing that notes rather than those other notes? Well, you will refer to the partition. So you cannot explain why the music is played as it is played without referring to the partitions. But you can explain independently of the music why the partition is as it is. Well, because it was written by that composer, so on and so on. And you don't have to refer to the music being played to explain why the partition was conceived as it was. Same for the house and the blueprint. Or if you want to take my favorite example, if you want a more naturalistic example of a reversal, take the relation between the genes and the phenotype. Is my favorite example. So some people say that our genetic code is kind of a blueprint of many of our observable properties. And here you can explain the properties of the gene without say for something on my genes, without referring to my height or my hair color or my eye color. But you cannot do the reverse. If you want to explain why I have the eye color that I have, instead of having maybe better eye color or height or whatever, why do I have the property I have? Well, you have to refer to the genes. So it's the genes that influence. All right, this is the principle. What does it say in our case? To conclude, what does it say in our case? Well, if you want to explain, if Field's program fails, if you cannot nominalize, then if you want to account for the properties of the physical world, give an explanation of why space-time is as it is, or why to base the laws, why it curves in such a manner in the presence of matter, you have to refer to the models. But if you want to explain why there are such and such models, that such and such mathematical properties, you don't need to talk about physics or physical spacetime or anything like that. The mathematician can give you an entirely independent account. So they give you the axiom, say, of set theory, and then they derive all the mathematical facts which are assumed. Therefore, if you have accepted my principle in the intuitive cases, if you apply it now, what does it tell us? Well, the influence goes in the direction like of explanatory dependency. Therefore, it must be the mathematical models that we can account for independently that influence the physical world. We cannot account for independently. Thank you.
So, have questions now? If you have questions, raise your hand. I guess I should also ask you if so the plan after this is to go to the pub and then for pizza. So if you want to come to the pub, you do the pub. If you want to come to pizza, do you want to go to pizza? To go to pizza isn't the weird way. You want pizza? No, he has to raise your hand. Yeah, you want raise your hand if you want pizza. Yeah. Okay. Thank you. 1, 2, 3, 4. Oh, 1, 2, 3, 4, 5, 6, 7, 8. I got good. All right. Now you raise your hands for questions. Okay.
Otherwise, you can just leave in protest. No.
Otherwise, just start shouting and screaming. Yeah. Or 3. Go ahead.
Yeah, so thank you. Very good. I have a question on that sort of ambiguity you mentioned at the beginning between what you were calling effective causation and metaphysical account. You sort of, I think you were very convincing to me, at least, with regards to the rounding aspect of it, to the sort of explanatory dependency. That I find quite convincing. But I don't understand then why to leave sort of effective causation on the table. I think even the person you were citing at the beginning of the video, I suppose they were thinking when they were saying that, I suspect that they were thinking of more of effective causation, right? I think that in many of these cases, when we're talking about these sorts of things, maybe it would be useful to distinguish between those two. And so then my question would be, is there a reason you want to keep effective causation on the table? Do you think that there is a case to be made for it?
Mm-hmm. Yeah. Well, maybe I will just first respond to one side comment, then I will come back to the main question. So I think you're referring like to Balakov, right? When you said the guy from the beginning, right?
But science is not a sign any causal role.
Right. Right. So again, all right. So if you when he says science does not assign any causal rule, if you're a grounding guy, you might say, yeah, I agree. It's not causal. It's a relation of ground or dependence. But then the middle point is that the part I put in blue, it looks like I randomly put stuff in blue, but here it's when he says something I think stronger, so it's not dependent in any way. And when he says not dependent in any way, well, that seems to rule out some sort of also relation of other relation of dependency, maybe metaphysical dependency or ground or something like this. And I think this is important. So why do we care about whether mathematical objects influence or whether some physical facts depend on the mathematical facts. Well, we care about it, well, one, because it's intrinsically interesting, I find it interesting, but also because it has a connection to the debate about whether these kind of things really exist. So you have a point of view associated with Quine that says, oh, epistemologically, our attitude towards numbers, mathematical objects, whether they exist or not, whether how we know what they are like, is the same we should have towards electrons. And what people like Balaguer are interested in saying is, no, the two cases are completely different. They are completely different. Electrons influence things. Numbers, they exist completely separated from us. So it was really important for them, what they do is, doesn't affect anything here. And they justify a lot of stuff on this. So, that's why he says, oh, the picture that it gives us of the world, the picture that physics tells us, oh, it would be the same if there were no mathematical objects. Like, it would make no difference to what goes on in the physical world. So that's why, he seems to be assuming the stronger view, right? So that's why I think that, I think here is really excluding both views, the view you find congenial and the one maybe you find less congenial with effective causation. Now, going back to your main question, which is why leave effective causation as a possibility instead of going directly straight to some sort of vaguer dependence, metaphysical dependence? Well, two reasons I did best. One is that I actually think the effective causation is probably more plausible than metaphysical ground, but for kind of technical reason, because I think that if something grounds another, generally it's supposedly necessitated. So it would be a necessity that if you had these mathematical facts, then you couldn't have also the physical fact. So it could not be metaphysically contingent once you have the mathematical facts that you have the physical facts as well. And I don't think that's the case. I think that the connection between these physical facts and the mathematical facts and the physical facts they influence is nomologically necessary, but not metaphysically necessary. Right? That's why I actually think that the effective causation, which doesn't require such necessitation relation, therefore is more plausible. Another reason is just that my argument, like the argument I gave with the various exclusion of the various possibility, well, basically, the premise should take account both possibilities, because in general, if you have a connection, it could be either effective causation or metaphysical ground. And so in some sense, since I just wanted a disjunction, and my argument goes straight to that disjunction, if I just wanted them to restrict to metaphysical ground, I would have had to basically give the same argument and then do something else. But since what I'm interested in is just a disjunction for this kind of rhetorical reason, to contradict Balaguer, for instance, I was happy to stop at the disjunction and then do not enter into details of which one of the disjunctions we need.
Thank you for the talk. I might have a question, but before could we go back to this last slide in which you introduced the last principle?
Yes.
Right. Yes.
By the way, I suppose that I needed to show you this, probably not. Probably something somewhere in my contract as well, but that 1, 2, 3, I did it, so that's good.
Yeah, could you spend more words on this, because I see that if when I made the trivial, the everyday examples, I can see what you mean, that in a certain sense you go from, for example, electrology to math, and in the other sense you go from the music to the music itself. But I don't know if I see also this analogy when it comes to, for example, physical theories and mathematical models of materials.
Right. I think the question is, do you see, do you agree that the way a mathematical model represents a physical system is kind of analogous or similar to the way a map represents a territory or a partition represents a piece of music actually being played? This is common. It's not something that is particular to me at all. That's a very common view, which is sometimes called the mapping account of representation, plenty of names I could cite, right? We define this mapping account, and the idea would be the way they represent the mathematical model represent the physical system is the same kind of representation. You have this correspondence between pieces of the model with pieces of the target. For instance, in the map case, you have spots on the map. They correspond to locations on the territory. And say a relation between, like distance relation between points on the map would correspond to distance relation between points on the territory. So usually the map would be like, the idea would be like some kind of shrunken version of the territory. So that, if something has that distance on the map, then what they represent as say 10 times or 100 times or something like that, that distance on the territory. Same for a piece of music. So intuitively, the various pieces of ink on paper, they each stand for a note, right? And then where they are on the treble scale, whatever, they represent, the pitches, and you can the relations, geometrical relation between the pieces of ink reflects the relation between the notes actually being played. So what I'm trying to justify at the beginning is that the way a mathematical model represents is very similar. So you have the pieces of the model, the various elements of the mathematical models, they correspond each to some element in the world. And whenever they have these mathematical relations, they would always correspond to physical relations. So mathematical curvature corresponds to physical curvature, or the integral associated with trajectory corresponds to the time elapsed by moving on that space-time trajectory. So the first thing to accept is that we have the same kind of correspondence in this case. So the same type of representation, the type of correspondence, and roughly of the same kind. And then my idea was, let's analyze these other cases, and I give you a principle that works in those cases. So it tells you, that predicts in which way the influence goes. So it predicts correctly, let's say the notes, so the partition influences the music and not the other way around, but it also predicts correctly that it is the territory that influences the map and not the other way around. So it seems to work on all the cases that we have already strong intuitions for. So now if you apply it, you bring the principles to the case we are unsure about, and we just follow it, it seems to predict that it is the mathematical facts that influence the physical facts and not the other way around. And therefore, then I would extrapolate the principle, that case, apply it, and then you would have as a consequence that so mathematical models are like a blueprint, kind of a very Platonic idea this way. They are like a blueprint of the physical world, or maybe they are like the genetic code of the physical world. They contain information about the physical world, and we can only explain, apparently, the physical world by referring to the models. Therefore, it probably, by the principle, the models that influence the world and not the other way around. In the same way in which it is not it's not the phenotype of the flower that explains the structure of its genetic code, but it is the structure of the genetic code that influence the observable traits of the flower.
No, when I see the problem of the argument, until I don't know if I'm like very convinced on the at the point where we go from this principle, if we apply this principle to the case, for example, of general relativity and physical corresponding physical features, I don't know if I'm convinced that this principle works also in that case. And in that case, it is from the mathematical models of general relativity to the physical world, because in a certain sense it seems to me more like closer to the idea of a map, a territory, rather than the partition and the music. So that I think if you have something more on why it is that way, it's working with that precise case.
I mean, I consider it's a very appealing idea. So maybe even many of you were like waiting impatiently for me to arrive like at the obvious conclusion, which is we look at the physical world and then we invent the models to correspond to the physical world. I understand why it's an appealing idea, and kind of the point of this principle is to try to bring you away from this intuition. So, I mean, there's not much more that I can do, but I think like my first idea was just to familiarize yourself with some example of models and targets that are not like the map case. So the musical partition case, the house blueprint case, these are not even my example. I just clearly stole them from Plato, right? These are like the idea of where the models, like the ideas, right? Or the Timaeus of the model is what influences the world. So in his idea, like in the Timaeus, it's actually the Timaeus that speaks, but he says that the demiurgos is looking at the model and then is like modeling the world to correspond to the model, right? So the first thing I just want you like to maybe to see is, oh, actually there are some cases in which I can see the influence going the other way. So at least you can conceive like the other cases. And then once we have the question, so we see that the influence can go either from the model to the target or the target from the model. Let's see what the various cases have in common. And here, I don't know, you can reject this principle. I mean, I cannot force you at gunpoint to accept it, right? I'm just saying, this is a principle that seems to work well on the uncontroversial cases, and then I want to extrapolate it to the controversial case. What you can do, of course, is any philosopher's modus ponens is another philosopher modus tollens, right? And you can just say, well, obviously, if the principle gets wrong, this obvious case of mathematical models, therefore the principle must be wrong. If you want to do that, of course you can. So if you're just, if you have like super strong intuition that, it must be, the influence must flow, then you will just reject the principles. So there is really not more I can do except, as I'm doing, just repeating myself over and over. I don't know, maybe that can convince you, but I don't know.
Follow up on mine? Sorry.
Hi, thank you. Do you hear me?
Yes.
Okay, yeah, I just had a follow-up on this question because, I can see the appealing of the principle, but the examples you give are like very, very different. For example, like in the case of the blueprint or the musical score, those are kind of prescriptive things. They say how the house should look and how the music should sound, so how the performance should sound. While in the case of the map, and I believe in the case of the mathematical model, those are merely descriptive things. They say how the phenomenon we want to track looks like and how it should look like. So though I see though the principle seems like very, very nice, it seems to me that maybe you're forgetting this kind of distinction that might play a role when you look at the direction of explanation or causation. Thank you.
All right, maybe, thank you. Yes, so there is something clearly to that. I just would like to respond to two things. So whether or not there is these prescriptive elements in the cases, some of the cases I mentioned, there is still the fact that once the house is built, so we have a correspondence between the blueprint and the house, or we have a correspondence between the music that has been recorded and the partition. So once we have that, we find the correspondence, and we still need to explain it. As you mentioned, in those cases, we have a human intentional explanation. So the explanation will run like, okay, some agent had to look at the model, and the model then instructed them, or as you say, told them how to create the object, so how to build the house, or how to play the music. I don't think that this invalidates my example, but of course it might make you uneasy. So of course, Plato kind of took this to the limit, because of course what he said is that, okay, even in the case of the physical world, or I guess it is what he attributed to the character of Timaeus, but what Timaeus said was also in the physical case, we will have a prescriptive component. So what the mathematical models are is a prescription for the demiurgos on how to then go on and create the physical world. Now, I don't want to say this. I don't think that's warranted. But that's why my favorite example, and let me come back to it, is the example of the genome, and why I insist. Because in the case of the genes, which are sometimes said to be a blueprint of, say, an organism, that's just a manner of speaking. So the representation is real, the correspondence is clearly there, but it is not prescriptive. So it is not a case. It's a perfectly non-intentional, perfectly, if you want to put it like this, naturalistic example of how a model could influence by a non-intentional, impersonal process, the model influences the target. So my response would be, if you, forget about like the Platonic examples, which are kind of more common sense and maybe easier to understand at first. If you want the best analogy between how I think of the relation between the models and the physical world, think of the relation between the genes and an organism. That's a perfectly naturalistically fine example of how the model can influence a system. Thanks.
Makes sense. Thank you.
Follow-up? No more follow-up.
Hi, can you hear me?
Yes.
Thank you. So I think your argument about the asymmetric criteria is a local rejection for physical facts to ground or cause mathematical facts. But what about something like a global ground? So if someone says that the Platonic world are a human invention and human beings are physical beings, so then the entire mathematical world are grounded in physical facts that ground human beings. What do you think about this kind of global grounding?
Good. I assume that the globe, if we don't have the local one, then for sure, then the global one wouldn't help us either. I'm a bit hesitating because technically you could have a scenario in which we first invent mathematical objects, and then they take a life of their own, and then they start to have a feedback loop. But that doesn't sound, would be a very plausible scenario. So I don't know. My principle seems to me, so if as stated seem to
But for example, we can have a evolutionary naturalistic account of how how our like numerical cognition develop as human beings, as like biological physical beings, how that developed, right? Then when we have a rich enough like Platonic world, then we develop further like more elaborate physical theories to account for finer physical structures. But at the end of the explanatory chain are physical facts in this story.
Right, but the point is that we cannot explain these physical regularities, say, I don't know, the fact that regularities between the time registered by a clock and the gravitational field, so clock, when they tick slower or faster, depending on the gravitational field, this kind of regularities, it would seem that we cannot explain that without reference the correspondence with the mathematical models. So the idea is that, you know, if we try to explain, well, you could construct some sort of explanation of mathematical facts based on human evolution, but then either you get a circle. I mean, I'm skeptical of those anyway, but even if you do it, then you would have a circle because, I don't know, you would explain one thing by A by B and then B by A. So it seems to me that I'm skeptical of this kind of circular explanations, since I think we can be satisfied by taking the mathematical accounts as primitive, but we cannot be satisfied by just taking the physical regularities unexplained. I would be more satisfied with taking our mathematical accounts of mathematical objects as bedrock, and then using them in the standard way to explain regularities in the world that cry out for an explanation. So they are observable regularities that seem to demand an explanation. I don't know if it makes sense.
Yeah, I see what you mean. Although I'm not. Okay, thank you.
Thanks.
No, it's just about the ontology of numbers. Also, yes, you know, about mathematical facts, mathematical object. You are assuming realism, and what tendency do you assume structuralism about the mathematical object? So what about the correspondence then?
Right. Did you say truth realism or did I?
Structuralism, something.
Structure. Okay. Good. Well, I guess the way I formulated the thesis was, if our best physical theories are true, right, and if we cannot nominalize them, then blah, blah, blah. Well, to the degree that our best physical theories are Platonistic in the sense that they quantify over these mathematical objects, so if you formulate them precisely, they will say such. There exist numbers such and blah, blah, blah. There exist mathematical wave functions such and blah, blah, blah. Then, well, yeah, so they are realists. So on the Poignant picture, they are realists. So they talk about these things. And so if they are true, so we are assuming, yes. So as we are assuming that, well, if realism is correct, it's part of the assumption, meaning just, well, they exist and they are like our physical theories tell us they are, then we have these consequences. However, you know, the conditional itself is just doesn't assume realism. So you cannot get out of the conditional by denying realism. So I'm just saying, if realism is true and all of that and that, then we have this consequence. The conditional doesn't depend on a prior assumption of realism. It just says, if realism, then blah, blah, blah. So it's more a consequence of being realism about physics in a way that would also entail realism about a bit of mathematics too. I don't know if it clarifies a bit.
Could you please come back to the correspondence that you made between models of general relativity to the physical world that you meant.
Right.
Like my question is more something like at a certain point you say that we can map particles moving in the world with something, but I didn't understand with what in the physical the models that they will say something. I know that this like there are a bunch of options here and depends on the physics that you if you don't. I just wanted to ask you if you had something in mind.
Yeah. So these are like mostly based on the how Malamud presents the theory, but this example in particular is thinking like this. So the simplest example of a correspondence is this. So we assume that there are a continuum of space-time points. So we assume that the space-time points can be matched, let's say mapped one-to-one onto these manifold points, which are some mathematical objects. You can think them, you can construct the manifold, say by taking them, maybe they are tuples of numbers. Now, the first assumption is that there is at least such a bijection. It's very, very weak, but it's just the simplest illustration. But then we say that the theory is something strong. So you can imagine that we match, you can consider now curves in physical space-time. So there would be the trajectory of a particle. So if you take a particle and you look at, say, the set of all the space-time points that it has occupied during the history, maybe it would be something like a curve. And the idea is that, well, if you there is a correspondence between the points and of space and the manifold points, such that, well, by the correspondence, the trajectory will be mapped. So to a set of space-time points, manifold points, so mathematical points, maybe a collection of tuples, which are what? Well, they are the image of what is called a timeline geodesic. Timeline geodesic is a function from the real numbers onto the manifold, which is generally continuous, infinitely differentiable, something like that. So it's something that resembles the real line, but you like stretch a real line or a segment of the real line inside the manifold. This is the correspondence. So between the trajectory of particles and certain of curves like that. So a subset of those curves are the geodesics, which have some mathematical property, right? Is that in the right direction, or am I talking?
Yeah, but like my point was just that in a sense that like you say that in the models we have like mathematical points that's going to be that. And then we have space-time points in the sense that they are physical.
Yeah.
And then you say that you have trajectories of particles, but there is nothing that is particles. And so I was just asking, like, do you map particles onto, I don't know, the energy tensor, or I don't know if you had something in mind that was just a question.
Yeah. You're right. Yes. There are these paper, especially by Byron, these refinements in practical construct what particles mean in general relativity, sort of idealization. So it's true that literally probably particles are idealizations. At least point type particles, right? So if you probably are not, it's very hard to put point type particles in general relativity. But in a realistic example, what you would have would be something like a tube then, right? If you have some continuous mass density, it probably some of it is stretched like a sort of tube. And when they talk about particles, they try to translate talk of particles into, say, the limit of a tube that gets thinner and thinner, and they try to do some construction like this. But if you say, oh, well, you can't have point-like particles in general relativity, I guess probably correct. I could have taken out particles, say, and talked about, say, the trajectory of of a body or of a planet or something like that. Then it would not be exactly a curve, because it would have some thickness, I guess. It would be something more like a tube. But yeah, so this was maybe as you say, you're right that there are some tricky details in this example. But for more details, check out Malanen chapter 2, and then there's like an explanation of this question about particles, more detailed than the kind of end waving I'm doing now. Thanks.
Good question. I'll ask you a question.
Good.
So I'm not, so for the principle that you had up there for a while, it said something like, whenever there was a connection in the causal interaction, the direction of causation goes from the variables we can independently account for to the variables we cannot independently account for. So I'm a little less, I'm not sure I fully understand like the variables bit, but here's, I take it like a principle that's very similar to the one that you have that I kind of feel like I have a better grip on. Namely that whenever there's connection in the causal interaction, we should assume that the direction of causation follows the direction of or connection of fit that we can independently account for. So if like we have a way of trying to see how one gets from one place to the other, rather than direction of causation, rather than direction of causing and following the direction of fit that we can't independently account for. So like in the case of the territory in the map, it seems like we have usually maybe reason to think that we go from the territory to the map. Whereas like if you didn't know anything, you just had the land, you just had the thing, you wouldn't go to the map or the blueprint. So like sometimes it won't tell you anything.
Right.
But then if it's thinking direction follows the direction of causation follows the direction of connection or fit that you have to account for, it seems like in the theory case, you do have the kind of account for why the theory successfully describes the phenomenon. And then it seems like you should favor thinking that the theory is like primarily describing sorry, I forget how you were talking, the mathematical facts are describing the physical facts, so you should think that explanation goes in the direction of, not the direction that you want to try it, let's go to
Well, so what do you think? Please, no, please.
Really, the question is this a kind of fair attempt at making clearer a kind of principle you have, or is it mucking things up in a bad way?
Well, so you said the direction of fit.
Yeah.
Would that be like the direction of representation? What represents what?
Well, so that would be one kind of direction fit. Maybe ground would be another, or some kind of attempt at somewhat explanatory direction.
Well,
it's not.
I mean, given that it gives exactly the opposite result I want, I have a strong incentive to say that it isn't, right? So, okay, let me try to explain what I think the principle is. Suppose you have side by side, right, the model and the target it represents. And I think like the direction of explanation, I think, is probably the thing that is most conventional. So we take the model to be a model and the target to be a target, just because we are interested in using the model to learn something about the target. There is something deeply objective there. I think it's us that basically decide what we take to be the model. This what we are interested in learning more about, and what we want to use to learn more about. That's on us. The question I'm interested in is, we have this model, we have basically two things, it doesn't matter model and target, we have two things that correspond to each other in interesting ways, that do not seem to be just the result of a coincidence. They could, some cases, two stuff just happen to have interesting correspondences, but it's just, a chance. But we have already ruled out that. So we know that there is not two by chance, but these two things have corresponding properties. And the idea is we have ruled out other options. So we know that either the properties and the internal structure of that thing somehow influence the other so by a mechanism so as to make it the case the two correspond, or the other way around. It was the internal properties and the structure of the first that influence at a part in causing the other to come to correspond it, right? So, but we don't know which. Maybe I'm already losing you, but we already know that the correspondence we see between the map and the territory is not a coincidence. And either the map is structured the way it is structured because the territory is structured as it is, or the other way around. So the territory is as it is, so it has some of the properties it possesses because the map is structured that way, or the other way. Because it's not a coincidence, it's not a common cause, it's not non-causal explanation, yada yada. So the idea is, what are the properties of the variables? Why basically are the pieces of ink like they are? Why is this pieces of ink with the name Lugano on it that far apart from the piece of ink we've written Bellinzona underneath, and not like this, and not like this, and not like this? These sort of facts. There are plenty of facts about the map like this. Why is this region with little concentric circles, why is it like this? Of course, you might say there is no explanation, but usually there are some interesting irregularities. So there are facts that could be explained. And in the case of physics, I think, really cry for an explanation. But in the case of the map, there are like these facts about the map. Okay, what does can we account them? So explain how the ink gets distributed like it is without referring the territory. Can we give an adequate explanation? I think no. Ultimately, any explanation, if we try to make it complete, any adequate explanation will have to refer to the territory. That's the idea of if we want to account for the properties, the internal properties of that system, I will need to refer and basically explain it from the other, but not the other way around. Whenever we have that, well, then I think that we already know that there must be dependence. I think it flows in the same region as the say the same direction as this explanatory dependence. What is the idea? Well, I have all these regularities in the physical world. I have these intricate regularities between, say, the trajectory of the clocks I send around the Earth and the time they put back. That's what I'm interested in explaining. And the idea is I cannot explain these regularities without talking about the correspondence that, say, the solar system has with, say, the Schwarzschild solution or something like that, some mathematical model. I cannot give you an explanation for why the stuff is as it is, of these regularities in the world, without explaining it from the correspondence with this model. But if you ask me some question about why is the Schwarzschild model as it is, then it seems I can give you a satisfactory answer by just deducing it. Oh, well, if you assume set theory, then the existence of such a model and it has such and such properties. And the explanation has nothing to do with the solar system or the Earth or anything like that. Therefore, that's the kind of idea. Can you explain the intrinsic properties of the object, how the parts are arranged without using the correspondence? Well, the stuff you can explain independently of the correspondence, that's the stuff that would then do the causation, and the stuff you cannot otherwise account for, which would be a miracle otherwise, because you have no independent explanation. The only explanation is through the correspondence. That's the stuff that is acted upon. That's what the principle says. And I think it's kind of reasonable. I think the most reason we would reject it, if I didn't give you like the main controversial example, I just gave you, I think, the uncontroversial examples. I think most of us, I think, would just run with it. But I understood what I thought. Maybe you. All right.
You should probably call it a day, and it's the lights are kind of turning off on us.
Right, I just you haven't shouted at me, so that's great.
All right, well, let's thank you guys.